Okay, so in the last video, we talked about this phenomenon of Bose-Einstein condensation, where you can get millions of atoms cooled to essentially absolute zero, as close as you're ever going to get to absolute zero. And then a question you could naturally ask at this point is, once you do that, what do you do with it? Um, well, I have young kids, and physicists in a lot of ways are like young kids. So the reaction of physicists to getting Bose-Einstein condensation for the first time is pretty much the same reaction as my 8-year-old getting anything new, which is you get something new, you just poke it and see what happens. Right, so they looked at things like collective oscillations, where they give the condensate a push and watch it move back and forth and watch how the atoms rearrange themselves. They'd also look at sound waves. You sort of blast a hole in the center of the condensate and cause shock waves that propagate out, and that tells you what the speed of sound in the medium is, and that gets you a bunch of information about the physics of the interactions between the atoms. Other thing you can do is you can use the fact that this is a phenomenon that happens because these atoms have very long de Broglie waves, right? And so they're behaving like waves, and a thing you can do is try and see that wave behavior very directly. So this is an experiment done in the Ketterle group. They split their condensate in half, so they have two BECs. Separated by a small distance, and then they turn the trap off and just let these, they fall and they also expand. And those expanding clouds of atoms begin to overlap with each other. And what you see when that happens is in that overlapping region, right, these are expanding, behaving like waves. In that overlap region, you get interference happening. These waves interfere with each other and produce regions where the probability of finding atoms is much higher, the probability is much lower. You see these interference fringes as these things overlap. This is something that can be taken to a really extreme length. The group of Mark Kastovich at Stanford now does experiments where they take a cloud of atoms and they throw it up in the air, 10 meters up in the air. They have an enormous vacuum chamber in a tower, and so they can throw the atoms up so they travel 10 meters up in the air before they come back down to the lower level. And when they do that, they can do a thing as they launch the atoms that splits them into two groups, right? And they can end up with those two groups of atoms separated by 54 centimeters, separated by half a meter, right? So it's a big enough space between the group that goes higher and the group that doesn't go quite as high. It's a big enough space you could pass your hand through it easily, right? And when those atoms return back to the bottom of the tower, they still see a clear signal of interference between those atoms. They see those atoms behaving like waves, even though they've been separated by half a meter, right? Their quantum wave packets were separated by an enormous distance. And so this is a really cool demonstration of the quantum nature of things. Now, for our purposes, what we care about is that these are extremely low energy atoms, which means that you can hold them in fairly weak traps. And so you can do things like catching your Bose-Einstein condensate just in the focus of a laser beam, right? You can make these crossed optical traps where you take two lasers and you intersect them, and you have a region where these two laser beams come together. Makes a trap for atoms that's not all that deep. You need to start with very cold atoms to hold them in that trap. But this works great for, in these pictures here, either a sample of potassium atoms or, again, these rubidium-87 atoms that are the ones that we're really going to care about. You can also use light that's tuned not to the red of resonance, where you make a trap that catches the atoms in the bright spot, but you can tune to the blue of resonance and push the atoms away from your laser beams. And there's some really interesting experiments people do where they make confinement for the atoms by making sort of a hollow beam of light. They make a beam that's dark in the center and tune that laser to the blue of resonance, so it pushes the atoms away. And you make essentially like a soda can for atoms. You have a hollow tube that's round, and you have a couple of sheets of light on either side to cap it off. And you can make sort of a box for atoms. that just holds them, and that's a nice thing. This enables an even nicer demonstration of the wave nature of things. They took this box and they put another sheet in there that split it into two pieces, and when they pull that that other sheet out, these two Bose-Einstein condensates, one that was in the left-hand piece, one that was in the right-hand piece, as they expand, they overlap, and you get these interference fringes, which is really pretty cool. So these are the kinds of things you can do when you start pushing these around. You can also push things around with light on a much finer scale. You can make interference patterns with lasers that are intersecting each other at a small angle. You can make sort of standing wave patterns that exist in 2 dimensions or 3 dimensions and produce bright spots where you can trap the atoms that are separated by something like a wavelength of light. That's something you can actually take a picture of if you put a camera lens right up close to the sample. And this is called the quantum gas microscope. This is done by a bunch of different groups now have these things. This picture you see here, they show sort of a schematic representation of the grid of points where atoms can be trapped, and you see like a microscope objective right up above it, really close to where the traps are. That can be used to resolve single sites in this lattice. This green picture that looks a little like static, each of the dots in that picture, this isn't the opening credits of The Matrix, each of the dots in that picture represents a single atom trapped at one of these sites in this lattice. And you can use this to look at how atoms behave in these sort of lattice configurations, which has a lot to do with how atoms behave inside solid materials. So this is of great interest to people who study condensed matter physics and solid state physics. Has a lot to say about the behavior of superconductors, the behavior of semiconductors, and there's a whole bunch of fascinating experiments you can do with this. You can also do this with the kinds of atoms that are not bosons but fermions. There's a trick you can use to get fermions colder, and that's really interesting because those are particles that obey the Pauli exclusion principle. You can't have 2 of them in the same spot ever, right? And so you make a sample of ultra-cold fermions, it's going to behave very differently than a sample of ultra-cold bosons. And this is really fascinating to study with these gas microscopes because, again, you can resolve this atom by atom within this sort of simulated solid and see what happens. So these are tools that are fundamentally based on pushing the atoms around with the very weak forces you can exert with off-resonant light, and opens incredible possibilities for things. So that's sort of the basics of, that's how we get Bose-Einstein condensate. That's how we can use various tools and forces to push things around. Now, I just want to walk through quickly what the experiment is, this tunneling experiment that we're ultimately talking about. And it starts by making one of these Bose-Einstein condensates of, several million rubidium atoms cooled to essentially absolute zero. And then those are caught in an optical trap. Right, so a focused laser beam, they're trapped in the focus of that beam. They overlap with that another beam that's also a red detuned laser beam, so the atoms want to be where the light is bright, but it's not focused nearly as tightly. And this acts sort of like a wave guide, right, or a little like an optical fiber for the atoms, right? The atoms are going to want to be at the center of this laser, but there's a large space that it can travel through. So they're going to tend to want to travel along this laser beam. So what they do is they overlap these two things, and then they turn off the optical trap, and they can give the atoms a push. Before they do that, they set up a barrier potential, right? And that's a blue detuned sheet of light that's focused down, so it's very thin and fairly intense, and it's a short distance away from the optical trap. They turn off the optical trap. They give the atoms a push. The atoms are going to try to travel along that guiding laser beam, and they're going to move over toward where the barrier is. When they get to that barrier is raising the energy of the atoms when they're in the region where the light is. So that causes them to slow down, stop, turn around, and head back. except that barrier is very thin, so there's some probability that the atoms can tunnel through it and end up on the other side. And so that's what they look for, right? They allow these pushed atoms to travel down the guide, they hit the barrier, and then a short time later, they take a picture of the distribution of atoms and see how many atoms made it to the far side of the barrier. Right, so there are some atoms are transmitted, they tunnel through the barrier and end up on the far side. Some get reflected from it and they're headed back the other direction. So they can take a picture, and by looking at how many atoms made it through, how many got reflected, that tells them the tunneling probability. And we'll also be able to tell them something about what happened to the atoms during the tunneling process. So, so now we've sort of completed the second of our goals for talking about this experiment. Right, we started off talking about what is tunneling and why is it a signature quantum behavior. Now we've talked about how do you get atoms that are suitable to perform this experiment. So we can get atoms that are extremely cold using a combination of laser cooling followed by evaporative cooling that gets them to Bose-Einstein condensation. And then we have these optical forces at our disposal that we can use to push the atoms around and create a barrier for them to either reflect off or tunnel through. The last piece of this is going to be talking about how you get the clock to measure how much time they spent inside the barrier. And that's going to take probably 2 live lectures and several more videos. So I will stop here and you come back later for either the next live lecture or the next set of videos, and we will see you then.